All right, so welcome to our autonomous
You
strategy
good?
live stream. So this is presented by our team, SubZero, and Team Parallax Robotics. So if you guys want to introduce yourselves.
I'm Pratik from Parallax Robotics
I'm Neev Gupta from
18386.
Parallax Robotics 18386.
I'm Nikhil Prabhakar from SubZero 18275.
And I'm Nihar from FTC 18275. Right. So yeah, so let's just introduce our teams a little more. So SubZero, we're a fourth year team. We have quite a bit of experience, although we have like rookie numbers. We're based in Mason, Ohio, and we're actually ranked number 11 internationally. So, and here's an image of our robot right there.
And we are Parallax Robotics. We have 7 Power Stacker members and 2 rookie members, and we're also based in Mason, Ohio. And below is our robot.
All right, so
An overview of the slides
yeah.
presentation in this webinar today will be, first we'll show you some autos from
Yeah, so the first thing that we're going to be doing is showing some example autonomouses, just learning about like the different autos from past seasons. Then we're going to be talking about how you can plan your autonomous, what to look for and what to do. And then we're going to talk about some different techniques such as localization, PID, OpenCV for vision, and path following and trajectory generation. So if you want to move to the next slide.
Yeah, so now what we're going to be talking about is, because this is an autonomous webinar, we will be looking over some previous autonomouses from this season and seasons past, because there are some common things that we can see and that we will discuss. So we will be looking at Quantum Leap's autonomous for this season. You guys probably have seen this, but here's a look. There are some common
All right, so we're not going to really debrief this right now, but as you saw, they had a 128 point autonomous. They were able to do pretty much everything in the Ultimate Goal game. So now we'll be looking at Team Black Forest Robotics and their 5-stone autonomous from the Skystone season. So
Yeah, so these are all autonomouses that are pretty advanced for the season, getting 5-stone, doing a full autonomous. So these are all things that every team should try to achieve for. And we will be talking about how you can achieve that in upcoming soon in these next couple slides.
okay, so the last and final autonomous that we'll see is from the Rover Ruckus season, and this is Team 8680 Kraken Pinions autonomous. So let's just watch it.
And so if you can see there's some similarities between all these robots, whether how they drive or the mechanisms they use, and we will be looking over that very soon. Okay, and one thing actually before we move on, if you have any questions about anything in the slideshow, you can scan this QR code that's in the first slide, and it'll direct you to a link that you can ask questions in. And also the link is posted in the chat. So if you have any questions, we'll be doing a Q&A at the very end. So just put that there and we'll be happy to answer anything. So Okay, one sec. Okay.
Okay, so let's just talk about like what these teams did well and what allows them to score
So
as
yeah,
many
as
points. Yeah, go ahead.
Yeah, as Nikhil and Nihar were mentioning throughout this the videos, all these teams had some similarity in their autonomous, and that similarity was the efficient path. No matter what the challenge was at the time, based off of the mechanisms and how well they knew their robot, they were able to form an efficient path in order to get their highest scoring autonomous. As we could see in the Quantum Leap's the first video of Quantum Leap, they go from wobble 1 to the power shots, then wobble 2, and then shooting the ring stack, and then parking. If you look at it closely, that was a huge loop, and they were able to go all around the field in a loop, making the most efficient autonomous and not going over the same path, minimizing the distance that they travel and scoring the highest points possible.
Another thing they did is they paired series of tasks. So, for example, Kraken and Rover Ruckus, they scored the gold mineral from sampling. In Skystone, Black Forest Robotics moved the foundation while placing a Skystone. And ultimate goal, amongst other things, you can drive while initializing servos. You can move the ring to through your robot to your shooter so that you're ready to shoot when your robot stops and stuff like that.
Yeah, and the important thing is that you're moving at the maximum speed as you can go, and then also having like an efficient path. And then, so what Neve was talking about was like doing multiple things at once and like pairing different things to cut time. So something that we do this year in the Ultimate Goal game is that we have a hopper, basically, which we keep our rings in a hopper and then we shoot them, and we're able to raise our hopper while we're moving, and that just cuts an extra like half a second that we would waste like lifting it up and doing nothing. So that's just a way that we optimize our path.
So now we're moving on to the next slide. So I'll just go briefly over this, and then we can go into more detail. So first is like the risk versus points. So this is basically just talking about what your robot can do, the skill of the people in your team, and how much experience you have. So that's basically the risks of that. So basically, the reason we do this is because not every team can do everything in autonomous. So being able to weigh this out to see what your team can do, to how many points it is really important, and something that you should do especially in the beginning of the season. But because we are in the mid-season and many teams are redoing their autonomous or rebuilding their robot, doing something like this, even after a couple months, is something that you should do. And I strongly suggest doing this if you haven't already.
Yeah, one thing to look at especially or two things to look at are accuracy and speed. So, for example, the high tower goal versus the power shot, it takes a lot more, you need a more accurate shooter to consistently hit all 3 power shots just because it is a smaller target. Versus the tower goal, which you have more leeway, and so if your shooter is not as accurate, you might consider going for the high tower goal just because it's more you can get points more consistently through all your matches. And in addition, speed, it's really important to find a really good speed just because speed also helps determine accuracy. If your robot's going too fast, it can lead to a displacement of your robot, or your robot can find itself in not the right orientation.
Yeah, so like just a short like anecdote about our team. So we had a scrimmage like a couple weeks before our first tournament, and during that scrimmage we had an autonomous that would shoot power shots. And while power shots are actually like they allow you to score the most points compared to, you know, shooting in the high goal, our shooter was actually not super accurate, and that caused in a lot of penalties, and our score was brought down a lot because of that. And we tried to be a little too ambitious, you know, and after that we realized that we should change to only shooting high goal, and by doing that we were actually able to have a much higher scoring autonomous, and we were also able to double our points for our first qualifier, which was actually really cool. And our autonomous was 119 points at max, so that was obviously pretty helpful. So that was a really good call which we made, and I recommend you guys like take into consideration like what your robot is capable of doing and like what your skill level is, because you want to be as consistent as possible, especially in like in-person competition. When you're going to be selected in alliances, the alliance captains are really going to be looking for a team that can do something consistently and well, rather than only scoring a high amount of points a couple times, because scoring consistently is going to be what makes or breaks those semifinal and final matches. So that's something to really take into account.
Yeah, so the next thing we want to go over is path optimization. So one thing this includes is using FSMs, or finite state machines, to move multiple parts of your robot at once. And basically how finite state machines work are there's an event, and then there's like what you want to do after the event occurs. And so, for example, if you're detecting how many rings are in front of your robot, let's say there's 0 rings versus 1 or 4 rings. If there's 0 rings, you might want to just go straight to depositing wobble. Whereas if there's 1 ring or 4 ring, you might want to shoot rings and then collect rings. So sort of using finite state machines sort of to determine the order of events that you want to happen based on the environment of the robot.
Yeah, so like another situation that like you could use an FSM for is like, of course, like moving multiple things at once. So basically, like a real situation of this could be, for example, like moving your wobble goal servo to like a down position before you drop it off. So you could say, while I'm a couple seconds into my path from point A to point B, move to, so I might be in a state called idle, like a subsystem state of idle. Then once I'm like a couple seconds in, you could specify that number of seconds, then change the state from idle to wobble goal initialized, and that would basically just move the servo down. And you could do that, and that would be like while you're moving. So that just helps cut down a lot of time and gets you set to just directly drop the wobble goal off and then move again, instead of like wasting time just standing still. So again, we talked about like moving at your max speed without losing accuracy. Basically, you want to be moving as close to 100% power as possible, depending on what your robot is capable of. For example, if you have odometry, which we'll talk about as well, basically you're able to get a lot of accuracy through odometry, and that will allow you to move at a much faster speed than you might be moving with a drive encoder based autonomous. The next thing is reducing I2C calls and speeding up your loop time. We're not going to talk about this too much here, but basically what it is you want to be reducing the amount of like I2C sensors that you're using, such as like color sensors and IMUs. These basically slow down the read and write time of your your expansion hub sensors and everything, and that messes up a lot of things like your odometry, and it causes drift. So it's important that you're using the fastest loop time as you can get, as well as reducing these really slow read sensors.
Yeah, the last thing is... Oh, go ahead.
Okay, so yeah, the last thing is when we speed up many subsystems. This is kind of where we use the finite state machines. It's because we have to save time, especially in autonomous with 30 seconds, and 4-ring stacks do take a while. So being able to do multiple things at once is also a very good idea. And in teleop, this is what we call like teleop optimization, where you click one button that does 2 things, but 3 things at once. So like when you do your wobble, it grabs it and picks it up at the same time. That's some way you can use optimization, and it's very good for speeding up things in the end game. And it's very it's not hard to program. So if you are a new team to programming, trying to do that with teleop is a good strategy to boost your teleop and just get more points in that sense.
Yeah, and like this also means like, for example, like your shooter, like if you can get your shooter to as fast as possible, you can get it. It'll of course save so much time in autonomous, and it'll also save a lot of time for your teleop cycles. So that's just really important. Like for the ultimate goal game, you want to have a super fast intake, so you can get the rings in your robot as fast as possible, as well as having as fast as possible transfer and shooting. Looking back at like Kraken Pinion in the Rover Ruckus autonomous video, their slides are shooting up in about 0.5 seconds, and that's just something that makes them an amazing team, as well as having a super high scoring autonomous.
Yeah, and going off of that, when we say as fast as possible, that also means like as fast as possible, but making sure that your robot is consistent. If you can go as fast as you want, but if it's not doing the same thing every time, it doesn't mean anything. So like trying to find the fastest speed that you can possibly do, and still keep your program consistent. That's what you want to try to aim for.
Mm-hmm.
So yeah, this is an efficient path. So when we were looking at the videos, we saw how different robots moved in different paths based off of what they wanted to do. So basically, an efficient path is how you can move in a certain way without overlapping parts, so without having to go over the same path again. So for Quantum Leap, as I mentioned before, that would have been a loop. They went all around the ring trying to finish off all of their tasks, and that was able to have a high scoring autonomous for them. And then based off of the team and the robot that you've built, you're going to have a different path. The key to knowing what path that you want is knowing your robot. As we've said numerous times already, knowing the accuracy, consistency, and speed of your robot will help you develop a good path in order for you to get a high scoring autonomous.
Yeah, so if we give some specifics, something that happened to our team this year is that with our four-ring autonomous, it took a while to get it perfectly because we wanted to make sure we were able to get all the rings and all the wobble goals in time and efficiently and as consistent as possible, because that's important in autonomous. So we had many different paths, and something that we did this year is the way we made our path is that we first shoot all the rings, the 3 rings we have preloaded and the 4 rings that we have in the starter stack, because technically if you think about it, they're all condensed in one area. So if you do it like that, you'll be able to shoot all 7 rings at once, and then you can go for the longer path for the wobble. Because what we first did is we shot 3, and then we went to get the wobble, and then we came back, intake the 3, take the second wobble, and dropped it. It just took way too long. There's too many things happening at once. So we realized if we can just use our intake to just intake all 7 at the appropriate time, we'll be able to be efficient. And that is something that we really stand by, and it works for us.
Yeah, and the last thing we sort of want to cover on is the efficient path really determines on your robot. So for example, if you have a shooter that can adjust to height, you have more possibilities of where you can shoot from. So you don't have to shoot from right in front of the line. You can shoot from where you start, or if you're slightly to the left or right of the target goal. And then in addition, whether your collector or your shooter's on the same side. So like when we looked at the Quantum Leap video, their collector and their shooter were on different sides of the robot. So what they did is first they went to the wobble goal, and then they came back to get the rings, so that when they got the rings, they could just shoot them right away. I know for our robot, our collector and shooter are on the same side. So something that might be more strategic for us is shooting from our starting position. And if there are rings in front of us, we can collect those rings. And that might save time for us.
Yeah, sure. Okay, so now we're going to be talking about like vision. So vision is a super crucial part of the game that's often overlooked. And examples of this, if you don't know what it is already, is like detecting the starter stack height, and that determines where your wobbles are scored. And if you're unable to detect the starter stack height properly, you lose out on all of those points for dropping the wobbles. So, and even in the Skystone season, you want to detect which are the correct Skystones, so you can correctly place them on the opposite side of the field. And when you're looking at these top scoring autonomouses, they pretty much just get started right away in their path, and you don't really see them waiting to detect. And that's something which we notice with a lot of rookie teams or beginner teams with their autonomouses. They're just sitting and waiting like a couple seconds to detect in their autonomous, and that's just again wasting a lot of time. And we've just talked about this a lot, but you wanna do everything as fast and as efficiently as possible. And by detecting in the init period, that allows you to know exactly where you need to go when the start button is pressed. So what we're going to be talking about here is learning OpenCV. So OpenCV is a vision library which is often used in FTC. It's also used outside with like machine learning and a lot of other stuff. We're not really going to go into that, but I recommend you guys spend a couple hours learning OpenCV, specifically in the off season if you can. And so personally for me, I just took around 2 hours, and I just looked at the OpenCV documentation, and I was able to pick it up pretty quickly. I also looked at some other like example classes and stuff. And in this season, actually, I was able to create. We were able to create our OpenCV class in about 30 minutes, and we were able to get our vision like right out of the way because we had that past experience. And why OpenCV over like any other methods? Nikhil, if you want to talk about that.
Yeah, so we had a lot of experience using Vuforia last year, and it was such a hassle. It wasn't reliable solely for the reason of lighting, because if we worked in a basement last year and there wasn't many lights, so we had a lamp that was pretty like it was pretty varied, and in autonomous and FTC you don't want to have many variables on the field, especially something external like a light. And we didn't realize this until our first tournament. That was in a gymnasium last year, and we weren't able to detect whatsoever. And it got really annoying, and we were really confused why it didn't work. And we realized it was because of our detection, and it only detected very close to the robot. So we realized Vuforia is not the way to go. And something with TensorFlow, we never directly tried TensorFlow, but we've heard from many teams in our local area that it's such a hassle, and it's not consistent as well. And that is why we moved to OpenCV. It's something that's gained popularity recently, and it's very easy to use. As Nihar mentioned previously, how you can use it. It's very reliable, and it can detect from a distance, because right now in that picture you see at the bottom, our robot is against the wall, and we do detect. And Nihar said how like people wait in the very beginning to detect, but the way that you can really do this is through initialization. So using initialization as that period of detection is very important to save as much time as possible, and OpenCV works the best for that. And we're able to draw those rectangles that'll help us detect whether it's 0, 1, or 4 rings. And I would suggest going to OpenCV or switching to that, because you'd most likely have trouble down the road using Vuforia or TensorFlow.
Yeah, so OpenCV also gives you so much freedom. You can use it for like a lot of different things. Not only starter stack detection. I know some teams are doing stuff with like bounce back in autonomous, where they can shoot power shots and the rings will come down, and they can use vision to detect that. And so there's just so many possibilities with that. And of course, you can also like compensate for lighting. You can do a lot of stuff with that. Vuforia and TensorFlow are not very free in that sense. They're provided by the SDK, and they work by using a machine learning model, and that model is kind of restricting, and they've not really been tested very much. So I'd say to stay away from them. So.
Yeah, and another thing just to add, all the questions that you guys put will be answered at the end. So.
Yeah. Okay, so let's move to the next slide.
So the next thing we want to talk about is dead wheel localization. So basically what this is you have 3 dead wheels, or 2 to 3 odometry pods, and they're not powered by motors, servos, or anything, and they sort of just like are sprung to the ground, and they allow you to track the exact position of the robot. This can be either position, velocity, acceleration, or you can use all 3. So some of the pros are, so why you'd want to use this is how they work is they have an encoder attached to them, and they can track the exact movement of the robot. And why you might not want to use just robot power or the encoders on the motors is just because of the fact that your wheels can slip, and having these wheels as sort of a safety mechanism can allow you to more accurately track your robot's position. And then using the data that you collect, you can create mathematical paths to follow, and it also just gives you more options for different trajectories. But some reasons why you might not want to work with it, although we do highly suggest it, is it might be a little bit more difficult to program, and you do need to tune it, and setup time can be a little bit time consuming.
Yeah, so like we recommend, like if you're a rookie team or fairly new to programming, maybe stay away from dead wheel localization for now. But you can use a lot of the techniques which we've already mentioned, such as finite state machines. Game Manual 0 has a nice guide on it, which we'll also link later. And we'll be also talking about like PID in the next couple slides, and that's like a super powerful algorithm which you can use, and it's pretty beginner friendly as well. So yeah, just to recap, dead wheel localization is a form of global positioning. You can find your X, Y, and heading / orientation of your robot, and using that information, you can follow pre-planned trajectories, or you can just follow a path, such as pure pursuit, which we'll talk about later as well.
Yeah, and so another thing you might be wondering, like if you are a new programming team, a rookie team, and we say don't move towards odometry, another thing that you can do is use the encoders on your motors. That is something that our team did for our first 2 years because we weren't super advanced in programming. And so there's a lot of resources online for that, and it's very simple to use. It's just a brief summary of that. It's basically where you use the ticks that the motor gives you from the wheel, and you use that to move the robot. So if you say you want to move like 10 inches, there's a formula that'll be given that'll make it like transfer into ticks, and then you'll be able to move the robot like that. But one thing with that is that you can only move in linear motion, so straight and turn. You can't do any curves with odometry, and we'll be able to see more of these curving patterns in odometry in the slides to come. But just if you are a rookie team or something new to programming, you
Alright, so let's just look at a couple like sample odometry pods. Basically, as we talked about before, they're basically like these free spinning wheels, and they're attached to these encoders. So as you can see in the image, yeah, there's like these tiny encoders. The most popular ones right now for the price and for the quality are the Rev through-bore encoders, and those are the ones that we use. I think Parallax uses them as well. They're super nice and accurate for the price, and I recommend you use those if you're looking to create some odometry pods. As you can see in these different images, they all have different sort of holders or 3D printed pods, so they're pretty nice. And then they're also sprung, so if you can see in the images, they have these springs that are basically holding them down to the ground. And for example, if your robot is lifted up by accident somehow, if there's some sort of issue on the field, or there's maybe terrain in the game, your springing will help you maintain that contact with the odometry pod and the field, and it'll always continue to track your position.
Yeah, and how they work, if you have 3 pods, you'll have like 2 on one axis and then 1 on the other. And then the one by itself will sort of track your strafing in one direction, and the other 2 will track your movement in the other direction, and then also your rotation.
Yep. Okay, so we're just gonna go over this slide really quickly, but there's a couple ways you can actually like use your odometry in autonomous. So say you know your position, but like what are you gonna do with that? As we mentioned before, there's different ways that you can actually use this. So the first main library that a lot of people use is something called Roadrunner, and I'm sure most of you guys have heard of this before, but you may not know what it is. And it's basically a path planning and motion profiling library, and it gives you the localization code to actually find your position on the field, and it also has a bunch of other cool like utility classes, as well as it gives you the code to move in a spline path, to move in a line path, to do a bunch of stuff. And the main difference between Roadrunner and other options is that the paths are actually pre-planned, so the path will be generated beforehand, and it'll already store the information, such as what acceleration do I need to be at this point in the path, where exactly should I be on the field, all the information right there. The next option will be pure pursuit. This is a path following algorithm. We'll show you guys that in the next couple slides. And then we have go to point, which is basically where you specify a coordinate or a position, and you just call it as a method, and the robot will just drive to that point. So as I mentioned before, okay, Nico, you want to talk about it?
Yeah, so first we're going to be talking about Roadrunner. That's one of the 3 ways you can move the robot. And you can see in this video here that these aren't linear motions. These are all curved paths, and they are all pre-planned. So as he was saying, there are like libraries that you can use that'll give you like access to these Roadrunner. So you can just use that to make sure that like have the gist of it, because your robot is different than any other, so you'll have to modify it yourself, like the different things on your programs, like how your drivetrain is set up. And these are used by a lot of teams, especially this year, and many of the top teams are really good at how they use Roadrunner to get the best autonomous scores, because as I said, that these can like cut through paths. Instead of using straight lines, you can turn and move at the exact same time, which is something that we do to like get wobble goals and just cut down on our time. Using Roadrunner has those advantages like that.
Yeah, so actually our team uses Roadrunner for our pathing and our autonomous, and it's actually fairly easy to use. It has a pretty extensive tuning process, meaning that there's a lot of different variables that you need to have fine-tuned to make everything work smoothly. But once you have that done, it's pretty simple to create paths, and you can do a lot with it. It's a really powerful tool. Many top teams use it as well as many newer teams. And the main drawback that I see with Roadrunner is that it's slightly restricting. You're unable to do some things with it, but it's pretty useful for a long amount of time, like with your knowledge. And you could learn about it on learnroadrunner.com, and that was created by one of our fellow teams on the FTC Discord server, and it has really nice documentation on Roadrunner, and it has a pretty nice tutorial on how you can get it set up with your robot. So now we're going to be talking about peer pursuit. So this is another option that you can use with your odometry, and this is I didn't mention this before, but with the Roadrunner you can actually use it with your drive encoders. There is a mathematical formula that allows you to derive your position using the drive encoders. It is fairly inaccurate, of course, but you can still do that if you want to. With peer pursuit, you're not really given that code to find your position, and it's not a library either. It's more of just a path following algorithm. So basically you use these look ahead points which you specify, as well as a radius around your robot, or a circle around your robot, and that'll basically allow you to, it basically tells the robot when to turn and how to follow the path. This is basically not pre-planned, because as I said, you have this circle around your robot, and as you're following it, based on the things that the circle sees, such as an intersection between a point, it'll turn and do different things. So this is not gonna do anything with like acceleration. It's not gonna know any of that. It's just gonna do whatever you tell it as it's going in the path. It's considerably faster than Roadrunner because it doesn't require any motion profiling, which is basically a ramp up and a ramp down, which is a part of a pre-planned trajectory. And peer pursuit allows you to have more freedom, just because you're not restricted to a library in that sense, and you can really do whatever you want with it, and change how the algorithm works and different things. So it's slightly more advanced. There's not at this point there's not a lot of benefit to doing peer pursuit over Roadrunner, just based on the amount of time and effort. But if you're into learning something new and going more advanced, then I recommend you check this out.
All right, the next thing that we're going to talk about in autonomous is PID. Now, most veteran members or most programmers will know what PID is in context with FTC, but basically it's a type of control loop that's implemented through programming. So what it is an error mitigation system, which means that it aims to reduce error in the system, and in that case, it's a robot. So tuning each value in the code itself, or the coefficients per se, would have an effect on how well your robot is able to meet the target. So whether it overshoots it, undershoots it, or if it meets it in its exact value. The P command in PID, or the proportional command, is actually proportional to the error. Hence, that the bigger the error, the bigger that the correction is for it. So it's a direct relationship. The I value, which tends to be the least important in terms for FTC, is the integral value, and this sums the errors over time so it can correct for overshoot of the target. And then finally, the D value, which is a derivative. This dampens the P value over time. So as P value gets smaller, the D will go into more effect so it doesn't overshoot the target. Tuning these values in or close to perfection would oftentimes lead to having no I value. So it is possible to have a good or a closely tuned p-value and d-value in order to so you don't have to have an I-value. And basically behind PID, that was the more programmatical concept behind it. There's also a mathematical concept, which is like the formula, the calculus formula, hence the calculus names behind it. And if you're somebody who's interested in math, then it may be beneficial for one person to understand that, so you can see the mathematical aspects to it. And as said before, Game Manual 0 has a lot of this stuff on PID, odometry, finite state machines that you can go and actually get some more information and learn yourself, obviously.
Yeah, so with like PID, like it may sound like a lot with these like integral and like derivative terms, but it's really all conceptual. Like you don't really need to know anything about calculus. I started like learning about PID before I was even in like algebra 2, so you really don't need to know any math behind it. It's all like conceptual in your code, so it's decently simple to learn, and it's super versatile. Some uses of it might be driving to a target. So for example, in this case, your error would be the distance between your current point and the target point. And then you would feed that error into your code, and then the P, I, and D, they'll each output a value, and then you'll add those values up, and then that will be your signal, and your signal in this case would be your motor powers. And then you would just feed your error back into your loop, and then we keep on going. So that's one example. You can also use it for controlling your motor velocity. So for your shooter, I use it on our shooter this year. It's really helpful because with different battery voltages, your robot may not know that it's actually not going at the velocity that that you want. So PID will always try to get to the correct target. And then it also helps reduce the ramp down or the ramp up time that it takes after a ring has been shot, because it knows that it's lost. The error is really big, so it tries to reduce that error. And then you can also use it for controlling linear slide heights. Yeah, so that's just pretty much some uses of PID.
Yeah, and if you've used PID before, you know that it's sometimes like a lengthy process in order to tune the coefficients and try to get it as precise as possible. But like you could use like FTC dashboard, for example, like being able to see how close the graphs get to each other and being able to see if what you're doing is actually progressing towards your end goal or what you want it to do. But although it may take some time, it is highly recommended and it's highly beneficial in order to get the most accurate movements or positions throughout FTC.
Yep, and lastly, just to wrap things up, so we've given you the tools and ideas to sort of plan and craft your own autonomous, but it's really ultimately up to you to actually build it to your advantages and to your strengths. So use what you've learned in this presentation to sort of craft your autonomous, and also keep in mind that the little things matter too. So if you have time at the end of your autonomous, where do you want to place your robot? Also, where exactly do you want to place your wobble goals in the squares? And then, can you use rings bouncing back into the field after power shots to your advantage, whether that be in autonomous itself or collecting them right out of the teleop period?
Yeah, so a lot of what we've talked about is in order to get a high score, in order to do the best that you can in autonomous, is knowing your robot as well as you can, the speed, the accuracy, based off of the mechanisms that you've built, what it can and what it can't do, and what you want it to do. Being able to understand those ideas and what those concepts will lead you to a better path and finding a good, efficient path for your autonomous, and that will lead you to scoring as high as possible.
All right, so now we're going to be having our Q&A period. So if you want to scan this QR code, you can do that and just add your questions if you have one. I'll also send this link in the chat if anybody wants to send it. Let's see if I can send it on my phone. So
Okay, so while that's happening, we can start with our first question that was mentioned. These are all anonymous people, like we can't see who said it. But the first question is saying you mentioned path optimization and creating paths, maybe the shortest possible path. Is there any way to optimize the robot's path with the program? So this is basically just asking, like, so we talked about a lot about how you can use path optimization to save as much time as possible. So like, is there any way that we can optimize it with the program? So there's not really like a set thing that you can do to like see what is the most optimal path for your robot. The main way that we did it is that we saw what other teams we used. We saw what our strengths are, because it really just depends on what your robot is. If a robot can do wobble goal in 5 seconds, then you can emphasize that. But if your wobble goal takes like 25 seconds to do your high goal, then you just have to work with that. So it's really just dependent on what your robot is. But trust me, it will take more than 1 or 2 times to get your most optimal path, or whatever you think is the most consistent. So creating diagrams, I would say, is the best way to do that. It helps you keep track of what you've already done and why it didn't work. And you will be creating a lot of autonomous paths over the course of this season. So just creating it on your own as a team is the best way to do that. So to answer your question, there really isn't a program that can find out what is the shortest possible path. But you can find out if you are taking too much time, too much distance to get somewhere from one point to another.
Actually, I just want to go off of that. Like, you kind of I think I know where you're getting with that, like with the person who asked. So if you have a way to know where you are in the field, there's definitely like math that you can use to figure out like what exact, like the shortest distance between different points. And like, for example, like if you're using like a spline, which is a piecewise function curve, and you can like interpolate that curve by using different points. You can add those points based on, you know, different distances and all this stuff, and you can optimize your path using that. But otherwise, like, there isn't like a super set in stone way that you could just have your program like autonomously figure out like the proper path. Usually like a human decided, like if by you experimenting with different things and like checking out the field, that's probably the best way to do it. But there, you can use it, like you can optimize your path using AI though. So okay, so the next
going off of what you said a little bit, like it's also not program is possible, but like like a human being able to see that based off of like what we said, being able to know your robot, what you built, how well you programmed it, being able to tell that will be the key in order to figure out what path is the best for you guys and the way you can get your highest scoring autonomous.
Yeah. Okay, so the next question is it absolutely necessary to have odometry pods for path planning, or is there a way without? So yes, there's a couple ways that you can path plan without odometry pods. Of course, odometry or dead wheel odometry is only one form of localization. One other method that some teams have been using now is something called VSLAM, and you can buy this camera called the T265 by Intel, and it's basically this camera which has its own code inside of it, like it's already given, and it'll figure out the X, Y, and theta position using vision. So the camera's fairly expensive, but I think some teams, like quite a few teams, have bought it and they've made it work. You can pair that up with like Roadrunner or your own system and have it work pretty nicely. The only thing is, with in-person matches, I think it would be slightly, it might not work as well, but I don't think a lot of teams have tested it out yet, but that's definitely one option. The other thing that you can do is, like we mentioned before, you can use your drive encoders. There is code and math to find your position on the field using your drive encoders. Of course, this will be less accurate than odometry, just due to the encoders not being as high quality on the motors, and there's slippage. There's lots of little small discrepancies that can mess it up, but it's definitely better to use a localization with your drive encoders than just using your pure ticks and doing something with that. So anybody want to add anything to that?
I think that was said pretty well.
All right.
Yeah.
Okay, so the latest question which we have is, do you have any sample code for creating a shooter flywheel PID? Okay, so so what you can do is check out Game Manual 0, and they have a pretty nice sample, just general PID class, and some people just create their PID in their op mode, and I recommend you just create a nice class for it that you can generally use for a lot of different things. So for the sample code specifically, check out Game Manual 0. There's also a library called FTC lib, and if someone wants to link that in the chat, they have pretty nice PID classes, and I've used them before. They've worked pretty well. So if you want to take a look at those classes, maybe use them for yourself or take inspiration to create your own class, I recommend you check that out. Do we have any other questions in the chat? Okay.
If no one has any questions, but like wants to discuss something like further than what we talked about already, or just like it doesn't have to be questions, just anything you want to say that we can go over more. Really, it's like up for discussion at this point.
Alright, so let's just give it like 30 more seconds. Yeah.
Alright, looks like there's a question.
Okay, so yeah, so Roadrunner and Pure Pursuit requires odometry pods, and there's no way to so you, like we mentioned this before, like if you're low on funds, like definitely like you don't need odometry pods. There's a lot of top teams have done like really nice autonomouses without them. Notably like 5064 Aperture Science at Houston Worlds, they didn't use odometry in the past seasons, and they were able to create pretty banger autonomouses. There's some other teams like Land Bros. They actually created a time-based autonomous, which is like kind of interesting, but they're able to have it work pretty well at Detroit Worlds. So if you have motor encoders, which you should, you can definitely use Roadrunner for that. That's probably the easiest method to go with. I would recommend to stay away from Pure Pursuit if you're in this live stream. I'm assuming you don't have a lot of knowledge about odometry and stuff. So Roadrunner is probably the best option to go with, just because it has a pretty nice structure to it, and there's quite a few resources for it now. So it's very helpful to use.
Yep.
Okay. Any more questions? If you guys have any questions about like SubZero, like our team's robot, or any thing that we use, then you can definitely like ask the question. Okay, so we have a question. Would you recommend using Roadrunner or Pure Pursuit? Definitely Roadrunner. Just because like if you're new to odometry, it's just gonna save you so much time. And like I mentioned before, the amount of benefit that you're gonna get by using Pure Pursuit is not gonna be like as much as the work. It's not gonna be like proportional to the work that you've put into it. So Roadrunner, no doubt. So, and I already said this before, but just check out learnroadrunner.com. It's a really nice website for documentation and everything. So if you want a nice like structured step-by-step tutorial on how you can use the library, then definitely check that out.
Oh yeah, just to quickly mention, like we've said throughout, if you have any more questions or want to learn more about PID, odometry, finite state machines, or anything else, you can go to gmzero.org and it'll give you a good introduction, and it'll teach you a good amount of those concepts as well as other building and more mechanical concepts too.
Yeah, so we just want to like introduce you guys to like these tools and these resources and these things that you can use, and then it's up to you to put some more time and research into it to actually learn how to do these things and implement it into your autonomous. So
And if you have any specific questions relating to your team, or if you need any help or want to do something together, you can always email one of our teams, and our emails are in the chat box.
yeah, so let's just give this like another couple minutes, and if we don't have any more questions, then we should be good. Alright, so looks like we don't have any more questions. Again, if you guys have any questions that aren't related to this presentation, then and want to talk to our teams, just shoot us an email. We have it in the chat. I can put this presentation link in the description of the video, so if you're interested in checking it out and just looking over it, then just feel free to do so.
Yep, and also feel free to contact us on Instagram or other forms of social media, and we'll be glad to help.
Thank you guys for coming and watching that. If you learned something new, that's good. We hope you can apply it to your autonomous and FTC. Hope you can score more, get better and better.